back to another video. Hope you all are doing fantastically well. In today's video, we're going to go over how do we perform a hypothesis test for the difference between two different proportions. So this is going to be the hypothesis test analog to what we did for confidence intervals. Remember in the previous video, we figured out how to do confidence intervals for the difference between two proportions. So this will be very, very similar except for one small little tweak, and we'll go over that now. So what are confidence intervals for, not confidence intervals, excuse me guys, what are hypothesis tests for two proportions? All right, so sometimes we want to perform a hypothesis test on the difference between two proportions. And so what we do is we collect two different samples, and we're going to analyze the difference between the two. This is called a two proportion z-test, okay? Because when we get our test statistic, it's going to use the z-distribution. Before we can get to that, as always, let's check our conditions. So since we are looking at two different groups here and collecting two different samples, what we need is an independent groups assumption, meaning one group doesn't affect the other group. Okay, so we need that assumption along with our regular assumptions for proportions. One being the independence assumption. And you guys know by now the way that we check that is via randomization. So hopefully we collected random samples. And also hopefully we sample less than 10% of the population. If those conditions are met, then we can say we have an independence assumption. And then there is the success and failure condition for proportions. And what this does is this ensures that we have a large enough sample size to mitigate any sampling variability or sampling bias. So in order to deal with the success and failure condition, I have to introduce a new proportion called the pooled proportion. I maybe mentioned this briefly for like 2 seconds in our in one of our confidence intervals videos, where basically you say you pool your proportions or you pool your values if you feel like your data is coming from a same population. Well, the deal with hypothesis testing, as you guys know, is that whenever we perform a hypothesis test, the null hypothesis is assuming that the two values are the same, right? What we're measuring is the same and there's no change, right? So if there's no change and they're the same, that means they come from the same population, right? And so for that reason, we actually have to pool our values for a two proportion hypothesis test, okay? So how do you pool your values? So what you do is, we have this new value, it's called p hat pooled. So it is the sample proportion, but we are pooling the statistics. So what you do is you take the number of successes in your sample one, add to that the number of successes in sample two, and then you divide that by the sum of the two sample sizes. Okay, so it's a pretty straightforward statistic to calculate there, but we have to use this for the two proportion hypothesis test. And just remember here, I have a little asterisk here. Remember that if we do not have the number of successes, we can multiply the sample proportion by the sample size and round up to the next integer. What I mean by that is, let's say in a problem they tell us, oh, 10 out of 15 people did this, and then 7 out of 18 people did this. Well, I know my number of successes. I know 10 out of 15, so my successes is 10. And then 7 out of 18, my number of successes will be 7. But what if they said instead, 35% of 200 people, like coffee, let's say. 35% of 200 people. So they're not telling me explicitly the number of successes. So what I would do in that case is I would take 35%, which is a 0.35, and multiply that by 200. Okay? All right. So that's how you handle situations where they don't give you the number of successes directly. You have to calculate it yourself, and remember the key is round up to the next integer. All right, so if you do your math, let's say I do 35% of 200, and let's say I get a number. I'm just making up a number here. Let's say it's 17.2. What I do is I round that up and make it 18. So our number of successes have to be a whole number for this to work efficiently. All right, so now that we have this pooled proportion calculated, what we do now is this should look familiar, right? For proportions, we always do n times p. We need that to be bigger than 10. Well, this time you're going to do your n1, the sample size of the first group, times that p hat pooled, that pooled proportion that we calculated. And then you do the same thing for n1 times 1 minus pooled. So when we do n times p, as we said earlier, when you take your sample size times your proportion, that gives you the number of successes. All right? just like what we talked about up here, right? Anytime I take a proportion multiplied by the sample size, that gives me successes. So then to get the number of failures, it'll be n1 times 1 minus p hat pooled. And so you repeat that also for the second group. N2 times pooled, p hat pooled, and then n2 times 1 minus p hat pooled. I need all of those values to be greater than 10 in order for us to successfully, pun intended, meet the success and failure condition. Okay. Once we have those conditions checked and we're able to continue, these are the steps that you do to perform a hypothesis test for two proportions. Let's be explicit here. This is for two proportions. All right, so the first thing we're going to do is we're going to write our hypotheses. And then right off the bat here, we see things are looking a little different. Because, remember, we're dealing with two different proportions, two different groups, and we are analyzing the difference between them. So what we're saying is that P1 minus P2, that difference is 0. There's no change between them. That is what the null hypothesis will always say. And I'll tell you this, sometimes, guys, sometimes you'll notice that instead of writing it as P1 minus P2 equals 0, if I add P2 to both sides, sometimes you'll see the null hypothesis written as P1 equals P2. And that's the same thing. Okay, so I just want you guys to be aware if you're using other software, other technology, you may see it written in that form. And then we have an alternative hypothesis. We have P1 minus P2 needs to be greater than 0. If it's a right-tailed test, P1 minus P2 is less than 0. If it's a left-tailed test, and P1 minus P2 does not equal 0 if it's a two-tailed test. All right, so those are hypotheses. Write the hypotheses, you check the conditions, and then here we go, folks. This is a formula. We need to calculate, I'm sorry for all the typos here. We need to calculate the test statistic, which is going to be a Z statistic here, okay? The test statistic is P1 hat minus P2 hat minus 0. So I'm taking the difference between the twos and I'm subtracting away my hypothesized value, which is going to be 0 for us, right? All of these are zeros. And then we are dividing it by the standard error, okay? So remember the standard error was in the two proportion confidence interval video. It was P1 hat times 1 minus P1 over N1 plus P2 hat times 1 minus P2 hat over N2, and we took the square root of that. It's the same formula, except for now we're just using that pooled version of our P hat. So it's very similar to what we've done before. It's just we're using a P hat pooled version. Okay? And then repeat the same thing with N2. So I want to be very clear, guys. There's a difference. I want you guys to know the difference. When we say P hat pooled, right, that is the number of successes of sample 1 plus the number of successes of sample 2 over N1 plus N2. When we start to talk about P1 hat and conversely P2 hat, that should be P2 hat. When we talk about these, now we are talking about within the individual samples, if that makes sense. So P1 hat is found by taking X1, let's say the number of successes of sample 1, dividing it by N1. This is X2 divided by N2, right? Where X1 is the successes for sample 1, and we have X2 being the successes for sample 2. So I hope that's clear. The very subtle difference between P hat pooled and P1 hat and P2 hat. Okay, after we've calculated that test statistic, you guys know the drill. We calculate the p-value, and then we make a decision based off of that p-value. If it's less than alpha, we reject the null hypothesis. If it's greater than alpha, we fail to reject. And then we make a corresponding conclusion. Anytime we reject the null hypothesis, there is significant evidence. Anytime we fail to reject or do not reject the null hypothesis, there is not significant evidence. So as we look at this, guys, you can see these formulas are starting to get a little crazy. I do want you guys to understand where this is coming from, but for me in this video, we're going to do all this in technology. We're going to use StatCrunch specifically, okay? So, but it'll be a great exercise for you to go through and see if you can recreate what we're going to do in StatCrunch, doing this all by hand, all right? So see if you could do that. But without further ado, let's jump into an example. All right. The U.S. Census Bureau tracks trends in minority ownership of businesses. A random sample of 2,000 Michigan businesses showed that 106 were minority owned. A sample of 1,000 Minnesota businesses showed that 21 were minority owned. Test with the level of significance, alpha equals 0.05, if the population proportion of minority-owned businesses in Michigan, P1, is more than the population proportion of minority-owned businesses in Minnesota, which is represented by P2. All right, so first order of business. Let's get these hypotheses going. So the null hypothesis is going to involve P1 minus P2. And since it's the null hypothesis, we set it equal to 0. Null always has an equals to. Okay? And then the alternative hypothesis is going to be P1 minus P2. But we need to think about this for a second. Okay? We're trying to see if Michigan P1 is more than P2. So, if we need P1 to be more than P2, that means the difference is that P1 minus P2, just subtract that P2 over, excuse me, needs to be greater than 0. That's what this means. If I'm subtracting P1 minus P2, and 1 is Michigan and 2 is Minnesota, let's make that distinguishment as well. Let's say 1 is Minnesota, and 2 is Michigan. What we're saying is if I need Michigan to be more than Minnesota, because I define my difference as P1 minus P2, I need that difference to be something positive, greater than 0. I need big number minus small number. That's how I get a positive value. Okay. All right. So right here we have P1 minus P2 needs to be greater than 0. All right, guys. It's very important that you understand how you identify or how your samples are labeled. Okay. If this was if they said, you know, Minnesota was 1 and Michigan was 2, then I would have this it would be the opposite scenario, right? So pay attention to that. Now the order of subtraction is not going to affect your p-value. You'll get the same p-value, but it will certainly affect your test statistic. Okay, so pay close attention to how your samples are labeled. All right, so those are the hypotheses. Next, let's check the conditions. So let's go through the independent groups. All right. Well, we're talking about businesses in Michigan, businesses in Minnesota. Certainly, it is reasonable to assume the groups are independent, right? Because they're in different states, right? So whatever happens in Minnesota shouldn't affect Michigan and vice versa. All right, but now we need to understand, we need to check to see if there's independence in the samples that we collected, right? So independence within the groups. All right, so we have to check independence between the groups, and then we have to check independence specifically within the groups. Well, we do that by random sample, checking the random condition, and the less than 10% condition. Well, let's think about this. Random. Well, they told us already that there was a random sample, right? So random sample means we have the random condition met, less than 10%. And then less than 10%, we're talking about 2,000 Michigan businesses in the entire state of Michigan. And we're talking about 1,000 businesses in the entire state of Minnesota. Those are certainly far fewer than the possible total amount of businesses in each of those respective states. Therefore, the less than 10% condition is met also. Okay? All right, what's next for us to do is we have to check the success and failure condition. Okay? In order to do that, we need to calculate this new statistic called the p-hat pooled, right? And what this is this is the number of successes from sample 1 plus the number of successes from sample 2 over the sum of the two sample sizes. Well, in sample 1, which is Michigan, they tell us that 106 were minority owned, out of a total of 2,000. So that means the successes for sample 1 is 106 plus, out of 1,000 Minnesota businesses, 21 of them were minority owned. So the number of successes in sample 2 is 21. And then we put that over 2,000 plus 1,000. We have 2,000 businesses in Michigan, and we have 1,000 businesses in Minnesota. 2,000 plus 1,000. Okay? All right, and so then that would equal, let's go over here to our calculator. Okay, we're going to do open parentheses. It's 106 plus 21, all of that in one set of parentheses for the numerator, divided by, open parentheses, 2,000 plus 1,000. Into, let's go 3 decimal places, we get a 0.042. Okay. All right, so once again, if you want to keep track here, X1, successes in sample 1 was 106. N1 was 2,000. X2 was 21. N2 was 1,000. Okay. So now to check our condition, I'm running out of space here. To check our condition, we need to take N1 times P hat pooled, then N1 times 1 minus P hat pooled, and then we repeat it now with N2. Okay, times 1 minus P hat pooled. Okay, we need all 4 of these values to be greater than 10. All right, let's start with N1 times P hat pooled. So we have a 0.042. We're going to multiply that by 2,000. So take 0.042 times 2,000, and we get 84. Okay. Now we're going to do the same thing, except for it's going to be N1 times 1 minus our P hat pooled. So that's going to be 2,000, that's N1, times 1 minus 0.042. And I know I switched my order of multiplication, but order of multiplication never matters. 1916. All right. So far so good. All of these are greater than 10. We're looking good. Now let's do N2 times P hat pooled. And N2 was 1,000. So it's going to be 1,000 times 0.042. That's 42. And then lastly, it's N2 times 1 minus that. 1 minus 0.042. And we get a really large number of 958. Okay? All right, so all of these are greater than 10, folks. So the success and failure condition is met. All right? So, moving along. Now that we have all the conditions met, let's calculate our test statistic and p-value. As I told you, we're going to do this in StatCrunch. But a good exercise is to see if you can do this. See if you can calculate the test statistic and the p-value by hand. And what I mean by hand is, yes, you can use your calculator to calculate the probabilities and things like that, but see if you could get that. Okay. But for us, we're just going to jot this down into the calculator. So let's go over to StatCrunch, okay? So how do we calculate this two proportion z-test? So what we do is we go to the stat submenu. Let me zoom out just a little bit. We go to stat, we go to proportion stats. We're going to go to to sample this time, and we're going to do it with summary. We have the summary data, okay? And, well, it should look familiar. Right? This is like the third time we've kind of seen this, right? We saw this with hypothesis, or excuse me, we saw this with confidence intervals, and now we're seeing it again with hypothesis testing. So the number of successes from sample 1. Sample 1 is defined as being, Michigan, right? Minnesota, excuse me, Minnesota. So the number of successes from sample 1 was 106. if you recall. So 106. And our sample one size was 2,000. Okay. Now let's go down here, and we're going to use X2 as the number of successes for sample 2 is 21 out of 1,000. Okay, so I'm hoping you know where these values are coming from, guys. All right, we're going to perform a hypothesis test. What else do we have? Perform a hypothesis test. We have our null hypothesis being H null is P1 minus P2 equals 0. That is correct. And then we have our alternative being P1 minus P2 should be greater than 0. We're trying to see if Michigan is more than Minnesota. Or excuse me, if Minnesota is more than Michigan, right? So P1 minus P2 is greater than 0. All right, all we got to do is go down to compute. And there it is, folks. That is our statistics here, okay? First of all, notice I keep on saying calculator. StatCrunch is going to do all of that pooling stuff for us, okay? So it's going to go through and it's going to use that p-hat pooled formula when it calculates the standard error, okay? So yes, like I said, recommend go back and see if you can calculate the standard error and get this z-score that StatCrunch gave us. But our p-value is tiny. It is less than a 0.0001. Okay, so our p-value is tiny. So what's the p-value? The p-value is less than a 0.0001. Okay, and what was our test statistic? It was a 4.104. Okay. All right. So once again, you guys have seen this 100 times now, but what's happening here is we have a normal distribution of z-scores. All right. And we calculate that test statistic, which is a positive 0.4014, which is somewhere here. And we're saying just this tiny little sliver of area to the right of that. Okay. Remember, we're testing if P1 and minus P2 is greater than 0. It is a right tail test. We're saying that little tiny sliver of area is the p-value, and it's tiny. It's less than a 0.0001. So it is tiny. All right, so since it's super tiny, that means that our p-value, we're going to take our p-value and compare it to alpha. Well, our p-value is less than a 0.0001. It's tiny. And we're going to compare it to a 0.05. I mean, since it's so tiny, it's definitely going to be less than our alpha. So we're in the scenario where the p-value is less than alpha. Therefore, we know that we should reject the null hypothesis. All right, that's just our rule, right? Anytime our p-value is smaller than alpha, we reject the null hypothesis. And what does this mean? This means that there is significant evidence. In fact, we have really strong evidence because that p-value is so small. There is significant evidence that the proportion of minority-owned businesses in, let me get these states correct, sample 1 was Michigan. Okay, is more than, or excuse me, I'm sorry, sample 1. Oh, yes, okay, all right, confusing myself. Pay attention to what we do here, folks. P1, so 1 is Michigan. 1 is Michigan. So actually I made a mistake. I'm so sorry, guys. Made a mistake up here. So 1 is Michigan. So yeah, so pay close attention to how the samples are labeled. All right, so they wanted us to have sample 1 be in Michigan. It's more than the population proportion in Minnesota. Minnesota is sample 2. So yes, there is significant evidence that the proportion of minority-owned businesses in Michigan is more then the proportion minority-owned businesses in Minnesota. I'm just going to abbreviate that, okay? All right. Last little bit, guys. As I told you, remember, if you don't have the number of successes, so StatCrunch and any type of really technology, they need to know the number of successes. So what if they said, like I said, what if they said 30%? What if they said 30% of 195 businesses are minority owned, right? So what we would do is we would take 0.30, multiply that by 195. Let's see what that gives us. Times 195. That's 58.5. So what you do is you do 58.5, and remember, you always round up. So your number of successes would be 59. Okay. All right. So I hope that was obvious. But anyways, appreciate you guys watching this video with me. I hope this clears up how we could do a two-proportion hypothesis test using some technology. And I look forward to seeing you in the next one. Take care.